Okay, can everybody see the screen?
Yes.
Yes.
Yes, sir.
Okay, let's get started. All right, so single sideband communications. So our goal in single sideband communications basically is to, if you remember, we need to extract the intelligence. And we know that there is intelligence in the upper sideband and in the lower sideband. So here we're going to learn how to remove the carrier and one of the sidebands. Also, in this is going to be one of those big areas because in your lab, for lab 5, you're going to be actually designing your own circuits. I am going to be giving you parameters later, not this week, but later, and you're going to design a single sideband modulator, demodulator, and you're going to be testing it, make sure that the correct frequencies come out, that you get the correct intelligence, and also the carrier. So keep this in mind. This is probably going to be a bonus assignment. All right. Usually students do really good on this. It takes some time because there's a lot of work involved, but it's very beneficial for you. So here we'll just go through these terms for the single sideband communications. There's only a few graphics in here. It's going to be posted online, but if you want to take notes, that's fine. Just let me know, and I'll just pause until you finish taking notes. All right. So here we have the major types of single sideband systems. The single sideband, the standard single sideband, is a system where the carrier and one of the sidebands are eliminated at the transmitter. In other words, only one sideband is transmitted. Primary advantages are maximum transmitted signal range with minimum transmitted power, because when you think about it, if we're transmitting more the upper and lower of this, it's going to require more power. And then it's also the elimination of carrier interference. So these are some of the advantages of the single sideband system. All right, so another system eliminates one sideband and suppresses the carrier to a desired level. The suppressed carrier can then be used at the receiver for a reference or automatic gain control, and also automatic frequency control. In some cases, demodulation of the intelligence-bearing sideband, and this is also called a single sideband suppressed carrier. So you will need to know this. Please remember that all this stuff is testable material in the PowerPoint, because we don't have time to cover all the different types of frequencies and so forth as far as design is concerned, but you do need to know and understand the terminology of it. So another system is the type often used in military communications and is referred to as twin sideband suppressed carrier or independent sideband transmission. This type of system involves the transmission of two independent sidebands with each containing two different intelligence signals. Now, you're thinking, how in the world does this happen? Well, this takes place in the military because instead of wasting our transmission with one bit of intelligence, which contains the same information on the upper sideband and the lower sideband, there is also a way for us to transmit information on the same carrier that contains different information on the upper sideband and different information on the lower sideband. So this is a huge benefit for the military. It allows them to actually transmit more than one bit of information. I mean, you can use your imagination on here why this will be important, but getting more information out there as quick as possible in the military is a huge benefit. So this is a very good system here, but it does require power to do this. So advantages, again, the most important advantage of the single sideband system is a more effective utilization of the available frequency spectrum. In other words, utilizing only one of the sidebands, since both in an AM signal are of equal intelligence, which we've talked about many times already. The second advantage of the system is that it is less subject to the effects of selective fading, which is great. We want to make sure that our selectivity is good. In the propagation of conventional AM transmissions, if the upper sideband frequency strikes the ionosphere, and is refracted back to the Earth at a different phase angle from that of the carrier and lower sideband frequencies, distortion is introduced at the receiver. In other words, distortion can be so bad that the signal could be completely lost. So we talked about having repeaters. Now I know this is going up into the ionosphere, but we've talked about having repeaters and the importance of, as the further you get away from the signal, the less the amplitude of the signal is going to be, and also it's going to start degrading even more. So we need something to actually make sure that we keep that signal amplified. Hence, in cell phone towers and stuff like that, they're building more and more closer together so that they keep a strong signal wherever you might be. All right, another major advantage of the single sideband is the power saved by not transmitting the carrier and one sideband. So this is reiterated, just a little hint. The advantage of this method is especially important in mobile communications systems. Less power requirements and weight reduction. So there's a lot of benefits to actually sending one sideband.
How does the other one pick it up if you're not sending the carrier?
Because what happens is that when we're sending this out, they have more repeaters to send out that same signal. So it has to be boosted often. So a lot of this—
I thought you said like the carrier was what station you tune into on the radio, right?
Yes, so the carrier. Yes, the carrier is part of this, but we're talking about not transmitting the carrier here. It's like in the military. This is more on the benefit of the military, because if they transmit let's look at it this way. If we transmit a carrier, usually it's a higher frequency, right? So if we're transmitting a carrier at a higher frequency, that means that signal is being sent out further. For the military benefit, if we just transmit one of the sidebands at a lower frequency, guess what? That frequency is only going to go into the area basically that military is in. So someone else, it's going to be more difficult to pick them up and to receive that intelligence information because it doesn't transmit as far. Does that make sense?
It does. The only thing is, I thought you needed the carrier for the receiver to tune in.
No, you don't need the carrier. The carrier is just something to help carry the signal a distance that's further away. Gotcha. There are limitations on this, okay? There are limitations on this. And if you look at the bottom part here where it says less power requirements, remember, power is key to getting the signal further out. So there's benefits for single sideband signals being sent out for just one intelligence part of it without the carrier. And there's also benefits of having a carrier involved with the intelligence. It's two different things altogether. Does that make more sense?
It does.
Okay. Yeah, I don't want you to get confused that you always have to have a carrier. But as far as we're concerned, we're going to be working with carriers as well. These are just some of the advantages. All right, so peak envelope power. All right, a method used to rate the output power of a single sideband transmitter. The pilot carrier, the suppressed carrier end the single sideband. The carrier is reduced to a lower level, but not removed completely. And then the twin sideband suppressed carrier, the transmission of two independent sidebands containing different intelligence with the carrier suppressed to a desired level. All right, independent sideband transmission, another name for twin sideband suppressed carrier transmission. So it's just synonymous with twin sideband suppressed. Balance modulator, the modulator stage that mixes intelligence with the carrier to produce both sidebands with the carrier eliminated. Again, this is removing the carrier. Double sideband suppressed carrier, this is the output signal of a balanced modulator. And all this balanced modulator and all that stuff, you guys are gonna be doing heavily in your lab. So you're gonna learn a lot more about this. All right, ring modulator, another name for balanced ring modulator. The lattice modulator, another name for balanced ring modulator. Like I say, it depends on who you work for as to what the nomenclature will be. but just keep that in mind that there are different names for different types of systems. Single sideband suppressed carrier, all right, a system that eliminates one sideband and suppresses the carrier to a desired level. Independent sideband or twin sideband, so suppressed carrier. This system involves the transmission of two independent sidebands, again, military, each containing different intelligence with the carrier suppressed to a desired level. Vestigial sideband, a type of transmission used for television video. We have our amplitude compounder, a single sideband, a newly developed system used to compress the amplitude of the intelligence signal before modulation through the use of a pilot carrier. Okay, pilot carrier, the suppressed carrier in the single sideband, the carrier is reduced to a lower level but not removed completely. The crystal filter, commonly used in single sideband systems to attenuate the unwanted sideband. It is able to pass a very narrow band of frequencies and are available with a Q as high as 50,000. And remember, the higher the Q, the better selectivity, and also that crystal oscillators are the most efficient oscillator because they very seldom have any effect based on heat and stuff like that, but they are more expensive as far as oscillators go. So if you're designing a system with that's you're going to use for transmitting and receiving and so forth, almost all systems today are made with crystal oscillators because they can be cut to a very, very precise frequency. All right, ceramic filters utilize the piezoelectric effect just like the crystal, but are more rugged in construction, smaller in size, lower in cost, and a Q up to 2,000 instead of 50,000. So a Q up to 2,000 is actually pretty good. All right, but these ceramic filters are a little less expensive. The shape factor ratio of the 60 dB and the 6 dB bandwidth of a high Q bandpass filter, and you will be designing your high pass or high bandpass filters in your lab and also in your bonus question. Now, when it comes to bandpass filters and low pass filters and high pass filters and so forth, all these we covered in the beginning and also in your previous class for analog 2. Remember, you will be using passive components when you create these bandpass filters and these other filters. That is what the majority of companies use when they build different types of filters for their clients. They are more precise, I should say, and they are also easier to keep. They're better when it comes to the rigidity of it because some of these filters get placed on aircraft, jets, and stuff like that. And when you talk about pulling a lot of G's on an aircraft, then you don't want these components to flex or bend or anything like that. Okay, you want them to be stable. So when it comes to ICs are a little bit different, and then we use the 741 op amps previously in your last class to create filters, but we will be using the passive filters. Thank you. So we'll be using the passive filters on this. Everybody understand what the passive filter components are? You guys don't remember the filters we did in the beginning of this class?
You mean the high pass and low pass filters where one gets...
Yeah, what kind of components, Thomas? What kind of components were they? All right, guys, you gotta remember this because you're gonna have to whip out your formulas also when you start doing this. You're gonna need to know your formulas on how to calculate for a bandpass filter, a low pass filter, a high pass filter. But those were all the things we did with the passive components, such as inductors, resistors, and capacitors.
Oh yeah, yeah. Okay.
Okay.
Thanks.
So
Sorry.
make sure you have your notes on all that. All right, and then we have the ripple amplitude or peak to valley ratio, a variation and attenuation of a sharp bandpass filter within its 6 dB bandwidths. All right, the phase method, single sideband generation offers the following advantages over the filter method. So there is greater ease in switching from one sideband to the other. The single sideband can be generated directly at the desired transmitting frequency, which means that the intermediate balance modulators are not necessary, which is another component that would be not applicable for this, and it'll also save money and weight. Lower intelligence frequencies can be economically used because a high Q filter is not necessary. The major disadvantage of the system is the 90 degrees phase shift network required for the intelligence signal. So anytime we have to have any phase shift on our signals and stuff, then that always gives us the opportunity, or it always has the chance of creating interference or static in our system. So this is a huge disadvantage. So keep that in mind when you think about these phase methods. Okay, so here's an example of a single sideband filter. So what we're going to do here is we're going to look at this for a second. All right, let's take a look at the information first. The above is the results of an output of a balanced modulator. The carrier has been removed. As you can see, there's nothing here. The carrier is gone. Okay, leaving the two sidebands. We have our lower sideband and our upper sideband. The purpose of the single sideband filter is to remove one of the sidebands, or one of the bands containing duplicate of the other, which we know that both this here and this here contain the same information. The result will be a much greater reduction in power for the transmitted signal and fewer harmonics, because we're getting rid of either this one or this one. Now, side note, keep this in mind. When you do your work on your bonus question, it does not matter to me if you decide to remove this side or this side, as long as one of these sides are coming through, because they will both contain the same intelligence information. All right, so keep that in mind. It doesn't matter. If you like, the lower frequencies passing through, that's great. If you like the uppers, that's great as well. All right, so now what we have here is, after the carrier here has been suppressed, we have basically a 200 hertz gap between the lower sideband and the upper sideband. So, and this is important because we do not want this and this to be super close together, because what happens is that if these get too close together, then we get contamination. So we have to keep these separated. And that's why in this case right here, there is a 200 hertz frequency range between this one and this one as far as our intelligence is concerned. Also, when we do our example today on our calculations, we will be using this value here of the 200 hertz that separates the two. Okay, so keep that in mind. All right, continuing on. So here we have our frequency range for the voice transmission. I told you this before, but when it comes to voice transmission, we have a range of about 100 hertz to 3 kHz. Now, I know some people can talk lower and some people can talk higher, that's fine, but this is an average. Okay, this is an average. Therefore, the upper and lower sidebands generated by the balanced modulator are separated by 200 hertz again. So that number we'll be using in our calculations in a little bit. So just keep that in mind. Now we have a breakdown of the entire single sideband transmitted block diagram. So here we have our, what is this?
That is a...
All right, who said the intelligence, right? And I just said earlier that our frequency range for human voices is around 100 to 3K. So that's pretty much 2K is right in there without a problem. So this is our intelligence. Coming into our Class A amplifier, and we're gonna break these down here in just a little bit. Then into our balanced modulator, and in this case, we have our oscillator, which, like I said before, this, even though it doesn't matter, it's a 9 megahertz, but it is a crystal type oscillator, because it is the most efficient type of oscillator. Then we have our balanced modulator, and coming in, we have our 9 megahertz right here, which comes from our carrier. And then we have our plus or minus 2, which is the upper and lower for our intelligence that's coming in. Going into our filter and amplifier, here we have removed the lower, and now we have the upper coming out. Then we have it going into our medium frequency balance modulator, which in this case, we have a different oscillator, and this is a variable shift, okay, to the desired frequency of 6 megahertz. So we have 6 megahertz here. 6 megahertz, if we shift it to that 6 megahertz, we now come out with a value of 2.89 or 2.898, and also the 3.102 megahertz. Then this is fed into our linear power amplifier, and then it is sent out on our antenna here, and we are now transmitting our 3.102 megahertz signal. Okay, so we have, we're going to break this down, so don't worry. And then also you're going to be doing all this kind of stuff in lab, so you'll get a lot more familiar with it. Just know that this is the overall block diagram for the single sideband transmitter. So the operation of it, as we break it down, the intelligence signal is amplified by a Class A audio amplifier. This is to ensure the integrity of the signal to be transmitted. The carrier is now combined with the intelligence signal, which we just saw within the balance modulator. Remember, the purpose of the balance modulator is to remove the carrier and output only the 2 sidebands. Then we have the output of the balance modulator will now be sum and difference of the 2 signals, which we saw the 9 megahertz and the plus or minus 2 kHz, which was our intelligence. And then next, the 2 sidebands will be applied to a filter, which in this case is a high pass filter, which we just saw. And then the output of the filter will now be applied to a medium frequency balance modulator, which will mix the new conversion frequency and the new carrier frequency. So we have a new carrier frequency here, which is actually less than before. The output of this balance modulator will generate 2 new sidebands, which we saw. The result of the new 3 megahertz carrier, which is a reduction of the 9, is derived from the variable shift medium frequency oscillator. Finally, these 2 sidebands, these 2 new sidebands will be the input of the linear power amp, or the amp, which will be used to filter one sideband, allow the other to pass. In this case, a high pass filter is being used, and that is what we saw in the output of that antenna. All right, any questions? Any questions on this? That is everything for our PowerPoint. Any questions?
No.
On the block diagram. Oh, go ahead. Whoever else was talking, go ahead and answer your question.
I was gonna say, could you go back to the last slide real quick?
Yeah, this one?
Yeah, I need to get that real quick.
Yeah, sure, go ahead.
When you're done with that, go to the block diagram. How did we get from
Good.
half of whatever, like 900 or whatever, how did we get from that to the 3000?
Okay, so here we introduced the 9 megahertz, right?
Right.
Okay, so we had our 2K up here. This became a positive upper and lower sideband. Of course, we know that, you know, this is the sum and difference, right?
Yep.
Okay. Then we had it coming into our medium frequency oscillator. So here, remember, we have the high pass filter. So we designed and built a high pass filter to allow this frequency to come through, which is what is inside here. So I got rid of the lower part, or I can say the difference, right? The difference side of it. So I come out with the sum side of it. Then I introduced this 6 megahertz, this new 6 megahertz frequency oscillator. And in this case, since we introduced this new one, this 6 megahertz is going to be taken away from this 9. That gives us the 3.
Gotcha.
Okay. And then of course it just goes all over again. We got the sum and difference. And then on our output, we have we're just outputting the high side of that frequency and getting rid of this. You see where that comes from now?
Yep. Yeah, I kind of thought that's where it was, just subtracting that 6, but I wasn't 100% sure.
Yep. All right, good question. So you might want to write this down as I'm doing it myself, so it'll save you some time later. It's still recorded, but you know.
Now, is that a 4 or a Y?
This is a 4 right here, Thomas. Is that what you're talking about?
Yeah, that's the one. Thank you.
Yep, it's 4. 4
4
delta
times.
frequency. I know it's hard to write on this sometimes.
Drawing or writing with a mouse is the worst.
Yeah. Yeah. All right, so our goal here is to find out what the value of Q is going to be. Okay, so we're calculating for Q. So this, let me change this. So this part right here is what I referred to earlier in our PowerPoint lecture. That delta frequency there, that for the change in frequency, that is going to be that 200 hertz. That 200 hertz that we talked about that are between those two sidebands. So that's 200 hertz. So all these other values, all the other values are fixed values except for the carrier frequency, which here in this case right here, we know what that is. It's given to you in the example. And the 20 is a fixed value that's in our formula, and so is the 4. So really all you need to do is plug these values in and let's see what we come up with for our Q. So in this first scenario, our Q is going to equal what? So whenever you get it, let me know what you come up with. Remember, the higher the Q, okay, the better the selectivity.
Is it going to be 184.88?
Nope. Check it again. Check it again.
$35.14.
Nope. Don't worry. I want to see if you what do you guys get it first before I explain it to you. Actually, it's all it is just making sure you understand how to input it into the calculator. What is this? What can you? How can you rewrite this part right here? You see where I'm circling now? How can you rewrite that instead of making it like 1 divided by 2?
Wants to take the square root.
No. No. What's another way to write that in decimal form just to make it easier?
0.5.
0.5, right. So you can write that as 0.5. You don't have to write that 1 divided by 2.
My main
I know
trouble
mine
is with
wasn't.
the log -1 and the decibels.
The log -1 and the what decimals?
The log -1 divided by 20. Do we have to?
That's all part of the log. That dB
Oh.
divided by 20 is part of the log.
Oh, okay. I see it. I see.
All right, try it again, Thomas. Chris, we're calculating for a value of Q based on this formula. See if you can come up with it.
Divided by 4 times 200.
3.4 something micro.
No. Wow, that would be pretty. I mean, when we think about the higher the Q, the better. That'd be a really extremely low Q.
Yeah, it would. But I don't know what I did wrong then. You just do the 250K, then you hit the log, then you do the 70 divided by 20 inside the log, right? Then you multiply that by 0.5, then you divide that answer by 4 times 200, right?
But then you got this. You got the 0.5, right?
Yeah.
Okay. So something was not entered correctly. I want to see if at least one person gets this.
Yeah. Yeah. So I did.
Okay.
So I did negative log of 70 like negative log of 70 divided by 20.
Right. Yeah.
After multiplying it by 250,000 kilohertz, I did the 0.5. I got 28,000. I got 28,117.
Nope.
85.1, 85.01.
85. No. Nope. How you doing, Tess?
Yeah. No.
I don't know what I'm doing wrong.
That's okay. I'll give you another minute or two.
All right, this is my last try. 287.18.
Nope. You guys making some good answers. Coming up with some
17,573.
Oh, Thomas, you rock.
Yeah, I finally figured it out.
All right. 17.
The 0.5 is not. I kept multiplying 250,000 with it, and that's why I kept getting the wrong answer.
17.57K. Way to go, Thomas.
If you guys want any assistance with that, look, it took me a while too. It turns out the 0.5 exponent, that's all just for the log. You don't.
Okay, so do you guys want me to show you how to put that in the calculator?
Yeah.
All right. So to start off with, we're going to go ahead and make a parenthesis here and start off with our 250K. Then we're going to make another parenthesis here. And now we're going to enter our, basically it's our anti-log, which will look like after you hit anti-log, you'll have a 10. And then, and that 10 up there is where you're going to enter the other values, which is, if this will write, hold on, can't get it to write. There we go. It's the 70 divided by the 20. Okay, that concludes that part. And then after that, we're going to be multiplying that times 0.5, or that's, I mean, it's going to be multiplied times 0.5, or the square root. Then we have all that divided by our 4 times 200. And then that's going to equal this. So try that and see if you come up with that answer.
I got the same thing.
do you mean you get the same thing?
I got the same answer when you said we got the same answer.
Oh, okay. Awesome.
Yeah.
Okay. Everybody else. Matt, Tess, Chris. Oh, Dennelson's back.
Now I must be putting something in wrong still.
Okay.
I got it now. We're good.
All right. Okay, so one more. Now we're gonna change this up right here. We're gonna get rid of this 250 and we're gonna change that to a value of 725 kHz. And our decibels, we're gonna change that to 90. And let's see what you get for the new Q.
When I'm typing that in there, do I close the parentheses up top of the anti-log before I put in the 0.5 or what? And
oh no, you're gonna arrow over one more time and then put that parenthesis after the 0.5. See this
0.5 stays up top, or
yeah, and then you
down.
just move your arrow over one more, and you're gonna get to be able to put a parenthesis around the whole thing, which is for this one, you know, these two sides.
Is the new Q going to be 161.16 kilohertz?
Nice work, man. Way to go, Anthony. 161.2 K. And that's just a Q value. That's not frequency. So we have a Q value of 162. So actually this 162 has a better rating than our previous one. So keep trying. Matt, did you get it?
I'm still working on it. So I closed that parentheses at the top of the 70 divided by 20. And then while it's still little, I type in the 0.5.
No, you're going to you close the parenthesis and then you're going to hit the up arrow and add that 0.5.
What kind of calculator do you have, Matt?
TI-84 plus CE or whatever it is.
Yeah, that's the same one I have.
Me too, but I have the special silver edition.
Wow, Thomas.
It's not that it makes any difference. I mean, the only thing I can do is just go back and clear every answer, not with the long, complicated way, but just go up to the previous answer, just hit clear a bunch of times.
Hold on a sec. Maybe I can try and help you out real quick.
All right, you get it, Matt?
Nah, I'll get it though. Keep going. I'll figure it out.
Okay, well, that's all there is for this. Then we're going to go to multisim.
All right.
Okay, can everybody see the screen with multisim?
Yes, I can.
Okay.
Yes.
So all I'm going to do here on this is just show you how to make sub-circuits, because in your lab, for lab 5 and also for your bonus, you're going to be making probably at least 4 sub-circuits within your primary circuit. Okay, so we're going to learn how to make sub-circuits. Has anybody made sub-circuits before?
Never. I don't remember. Or I don't think I've heard of them.
All right. Okay, so the first thing we're going to do, and I'm just going to make up, I don't know, whatever, but just to show you how to create them. You'll need to know how to do remember, this is where you'll actually be designing or building your filters that you are going to have to come up with and calculate for, as far as what values of a bandpass circuit or low pass circuit or whatever. And you'll be placing those inside your sub-circuits. Okay, so that's what the sub-circuits are used for. So the first thing you want to come up here is click on place. And if you guys can't see something, please let me know something. Place, new sub-circuit. All right, actually, you know what? Before I do that, I'm going to go ahead and bring up put a ground in here. And I'm going to go ahead and put a power supply, just a DC power supply. That's fine. All right. So now I have some components started, and this would be like my whole design here that I'm building as far as when it comes to your lab. You'll be building all these, putting all these components together along with subcircuits. All right, so go back up to place, new subcircuit, and I'm going to name this whatever you're going to name it based on the type of filter. Like if you were creating a low pass filter, you would type in low pass filter, or if it's a band pass and so forth. Okay, so I'm just going to say a cool test. Then I'm going to click OK. Then I got a little box I'm floating around with. So I'm going to hit click again, and there we go. So now I have my sub-circuit number 1, and it's called cool test. And right now it has nothing in it. It's just a square box. So I go to my square box in the middle, and I double click on it and open it up. And behold, you'll see some information here. And this is the hierarchical block sub-circuit. Here's my reference right here. I can change that if I want to, but I don't really care. And I'm going to go to open subsheet. When I open it, I got a blank screen. What happened was in my design area over here, this is the original area. It automatically created me another tab called cool test. And everything that I put inside here is going to end up inside this little box. So I'm going to go back to my cool test, and I'm going to just put some resistors in here. That's fine. Let's say 1, 2, 3, 4. That's good. So I got 4 resistors in here. And just to make this simple, I'm just going to hook them all up in series, nothing major. And like I say, whatever you design inside here, it's going to be working in the other part of the program, and it also functions in this program, in this area. So you can run tests in this area if you want to, or whatever. And I'm going to change these values. So that's 1K, change this one to 2K, 3K, 3K, and 4K. All right, so now I have 4 resistors, and I have 4 different values. So I'm going to keep that there for a second. I'm going to go back over to the design area. And when I do, you see I still see nothing. So it's really telling me that, hey, you don't have anything in there yet, but I really do. So I'm going to go back to my cool test area, and I need to do some things. So I'm going to go up here in order for this to work to place again, where it says place. And I'm going to go down to connectors. Now, there's several different connectors you can use, but I'm going to use the one and show you how to manipulate that one, which in sense you can manipulate any of them. I'm just going to click on the hierarchical connector right here. I click on that one, and I'm going to put a connector at this end, and I'm going to put a connector here, 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 and here. So I have 5 connectors. Now we need to label and identify what these connectors are actually for. This one, R1, is going to be used for our input. So I'm going to go ahead and connect it to R1, and I'm going to double click on the connector. And that brings me up a connector information box. So here I'm going to name this one, and this is important here. You need to name these because you need to know what they actually are on the other page. This one's going to be my input. I named it input, and the direction underneath here, I need to bring down this drop down and say, hey, this is an input. Then I click OK, and lo and behold, I have an input connector coming into R1. This one, of course, over here is going to be our output connector. So I'm going to label that one output. Go down to direction, label it as output, and click OK. And then I'm going to flip this horizontally and bring it down 1 notch. and connect it here. Oop, there. So now I have an input and an output. These I'm going to rotate 90 degrees. And then I'm going to connect each one of these to here. And then I'm going to enable these at the value like the R1, R2, and R3 position. So I'm going to double click on these. I'm going to name this one R1. And then as far as being an input or output, it can be either way. So I'm going to keep it as generic. And I'm going to click OK. Oop. Oh, I already have an R1 in there. Sorry. R11. Oop. Just to identify it, that's R1. Then I'm going to do the same thing here. This one will be R22. Generic. And then R33. Generic. All right, so now I have my input, my output, and 3 test points that I can use, generic test points, R11, R3. Now, keep this in mind. If I was to measure my voltage at this point at R11, it would be going in this direction. So I'd be here all the way to here. So whatever the voltage is across this one, and this one, that's what it would be. Same thing with here. R22 would be for this one, and then R33 would be just across R4 for the output. Now, in some cases, you don't really need to worry about having a ground in here. Like you guys know that when you're using multisim, it won't do simulations unless there's a ground. Well, this is all actually part of the other circuit. So now that I finished all my connections here, I can go to my design and look at that. I now have a sub-circuit with an input, R1, R11, R22, R33, and an output. And these are all actually simulation connections. So if I take my sub-circuit over here and I want to connect my voltage up to here, so I got my input here. Hold on a second. There we go. So I have my input there, and my ground, of course, is going to be down to here. But my output is going to be on the other side. So my output here is coming to the negative side. So if I went back to, uh-oh, what happened? Oh. All right, another thing you need to keep in mind is, just so you know, it didn't disappear, but if you look down here, the tabs, you only see the design tab. You're like, what happened to my other tab for the sub-circuit? All you need to do is go to the sub-circuit, double click on it, open up the sub sheet, and there it is. So you didn't lose it. It's still there. It just closed it out. So I go back to here, and basically what I'm doing is I'm hooking my positive side up to here and my negative side up to here, creating a simple series circuit. So I go back to here. Then I'm going to bring out a multimeter, and I will use the Agilent multimeter. And of course, we're going to run this at DC voltage because that's what we're using. And I'm going to go ahead and copy this ground real quick. Copy, and then put my ground up here on my multimeter. Now I can take my output or my lead from my multimeter, and let's say I want to measure the voltage from R11 or R11 all the way across the rest of these. So I'm actually putting my meter here, and I'm measuring all 3 of these, whatever value is across this. So when I come here, I'm going to run my simulation, and lo and behold, I have 10.8 volts from that point. So my sub-circuit is working properly. If I want to measure the value off of R22, same thing. I just move my lead. I have 8.4. And finally, across that R4 value, I have 4.8. And that's how we create a sub-circuit. So, and as you can see, a sub-circuit, any questions on this real quick?
No.
Okay, it's pretty straightforward, but anyway, but think about this. When you design circuits in multisim, you're gonna, you have a lot of space on here. So you don't want to just cram all this stuff into, you know, in your one space. You can actually create those subcircuits, and those subcircuits can be used to make modifications, for instance, to your frequencies. Like you might want to say, hey, I want to create a low pass filter. Instead of changing the, you know, going through and looking for the components and double clicking on each of them, just go to your subcircuit and make the changes there. Because when I go to here, as soon as I make a change here, like I'll change this R4 to 7K, I'll hit enter. And as soon as I go back to my design, that new value is now affected inside my subcircuit. So you don't have to worry about trying to update or remembering to update. Whenever you make those changes in the subcircuit, it automatically updates the subcircuit itself. In your lab, on lab 5, you're going to be ending up making 4 subcircuits within your primary circuit. There's going to be a lot of components that go into lab 5. And as a reminder, lab 5 is like a heads up on what's coming for the bonus question. So you really need to make sure that you understand how all this works, because you're going to be using bow plots, you're going to be using spectrum analyzers, oscilloscopes, and so forth. And also transformers and other components that you haven't used yet. But all that stuff is spelled out in the lab. So, but when you see those labs, these are the type of things you'll be doing. Any questions?